Hi, this is Dr. Justin Estrie, and this is week 3 of Poli-Sci 506, Computational Bayesian and Nonparametric Statistics. And today we're going to talk about methods for computational sampling, which gets at an issue that we started to touch on last week when we began talking about Bayesian inference. So Bayesian inference works primarily with posterior distributions. And last week, what we did in order to make a posterior distribution something we could work with is to think about combining a likelihood, which has a known analytical form of some kind, with a conjugate prior distribution, where the conjugate prior has a known analytical form, and the combination of the product really of the likelihood and the prior is itself a known analytically closed distribution. So, for example, we talked a lot about the normal and the binomial. For example, if we're using the binomial as our likelihood, then the beta is a conjugate prior such that the posterior of the combination of a binomial likelihood and a beta prior will be another binomial, technically a beta binomial distribution. But one of the main advantages of Bayesian models is that they can be very complicated. We can build very complex structures that don't necessarily have to conform to already pre-specified analytical structures, analytical forms. We can, as long as we can write down a posterior density of some kind, we can work with it. But the issue is we have to have some way of working with that particular kind of distribution. And so it becomes a topic of primary interest how we're going to get samples from that probability density, from that posterior density, if we can't write down an analytical form for what that density looks like. What do we do in that situation? As long as we can take samples from that posterior, it's going to turn out that we can compute the quantities we're interested in, like we can show joint and marginal probability density distributions, we can compute credible intervals, all kinds of stuff, but we need to be able to draw samples out of an arbitrary distribution. That's easy if, like last week, we know what it looks like. If the posterior is analytically known, no problem. We can just type D norm, or R norm rather, to draw a bunch of random normal samples. Let me say that again. We can type R norm to draw lots of samples from the normal distribution in Stata. That's the easy thing to do. But we want to be able to do that even when it's not a normal density. It's an unknown density, the density of unknown shape. That's a combination of a likelihood and prior, which does form a proper density of some kind, but we have no idea what it looks like. So this week, our primary topic is going to be figuring out how to take samples out of complex distributions and compute things we're interested in from them. It's going to really enable us to do much more with our Bayesian modeling in future weeks when we start to talk about dealing with complex. When we start actually building complex Bayesian models. So this is really step 2 in a multiple step process that will eventually get us to a place where we can do this kind of complex inference. So, without further ado, let's get started. So before we start to talk about how to draw samples from a complex distribution, I want to step back for just a moment and talk about some things we can do with these samples that we're going to draw. And one thing that we're going to do is compute probabilities, areas under a density. Specifically, we're going to compute probabilities that some parameter or estimated quantity of interest is in some range. Monte Carlo integration is a way of integrating over a density, including things like a probability density, over certain ranges of the argument, of the parameter, in this case theta. Now, there are lots of ways of doing integration. Some of them are simpler than Monte Carlo integration. For example, there are integrals that are analytically solvable, where we can just compute a quantity directly using the analytical functional integral. But as we've already discussed, one of the main points of Bayesian modeling is to deal with cases where the analytical form of the integral is unknown. So we're going to integrate over a posterior density. We don't know what the posterior looks like, and we still need to compute probabilities out of it. So what are we going to do in cases where we can't analytically solve an integral? And one key case of this is the multivariate normal density does not have a well-known cumulative density function. It's not analytically known what the cumulative density is for that particular function, a very important function, the normal. And so if we're going to compute areas under the multivariate normal integral, we're going to have to find some other way to do it. Monte Carlo integration is one of those ways. So here's what Monte Carlo integration does. It's a very simple idea. Take the density you're interested in, f of theta, and draw lots of thetas out of it somehow. Now, in R, or in Stata, but let's talk about R. In R, if you've done this before, if you've drawn lots of samples from the normal density, for example, you typed R norm, which is the function for drawing random variates out of the normal. It turns out that there are some complicated ways that actually happens underneath the hood. Jackman talks a bit about this. There are other readings I could show you where this is a real topic of interest in computational statistics. And we are going to talk about some ways of drawing samples out of a distribution in just a second. For right now, I'm going to assume that it's trivial to draw certain kinds of samples, and in particular, it's trivial to draw uniform samples out of the uniform. And we're actually going to build up from there. But for now, let's just say somehow, through some technique, we're going to draw a lot of samples of theta from f of theta. Okay. Then, if, for example, we wanted to integrate over f of theta between theta 0 and theta 1, all we would do is say, okay, I'm going to count the number of samples that are inside of theta 0, theta 1. And then I'm going to divide by the total number of samples. So think of there being some distribution here. Here's f of theta, and here's theta. And we drew a ton of samples out of this density. And you can think of like there being a sort of histogram of how many samples we drew in each bin of theta, something like that. And then if we want to integrate between, say, let's see here, integrate between here and here, we simply add up these histograms between these 2 points. How many samples do we draw between those 2 points, and then divide by the total number of samples we drew. The end. That's it. Now, I've depicted this with a histogram here. Obviously, that's not exactly how it works. We would not bin them if we were doing this. We would just count the number of observations in between these 2 lines. So you could really think of there being a bunch of points sort of all drawn all in here, stacked up. We would just count the number of points in between those 2 lines. That's it. That's all there is to it. It's a very simple procedure to explain. We're just taking a look at what a density looks like by drawing a lot of samples out of it, and then computing brute force averages or sums out of those samples. Pretty easy to understand and pretty easy to explain. The hard part comes in actually getting the samples. And as I alluded to, this can be a very complicated topic. How to sample out of a distribution is really, really complicated. We're only going to scratch the surface. Even in today's whole lecture, we're going to talk mostly about this topic and still just scratch the surface in what's going on. We're just going to cover a very few simple methods that are going to be the most commonly used methods that you'll use as a Bayesian statistician. So let's start with a reasonably simple procedure for sampling called the accept-reject algorithm. So the accept-reject sampling algorithm is a procedure that we can use to move from sampling from a simple distribution, in this case a uniform distribution, to sampling from a more complicated distribution. And let me explain just briefly how this works. So what we're going to do is we are going to create a proposal density and call that P of theta. And this should be something that we know the form from. We know the analytical form of this density, and we can draw out of this density. Now, I could just do this with all uniform densities, actually. I could either piece them together or just use the uniform in general. But there are other densities that are common that for us to use as proposals, such as the normal, the logistic. Anything that we can sample from easily in R or stata is a potential candidate as a proposal density. And of course, it's trivial to say this is not going to be equal to the target density that we're interested in sampling from. If we had an algorithm to sample from the target density, we wouldn't be bothering with this algorithm in the first place. So, right. Now what we're going to do is take this proposal density, P of theta, and create what's called an envelope function, which is just alpha, a constant greater than 1. So just to make a note of this, alpha is usually bigger than, at least this big or bigger than 1. Such that the envelope function is always bigger than the target density at every point theta. So what are we doing here? Well, it's easiest perhaps to see this in a picture. Let me take that back. Let me move this over here. Okay, so here we have theta, and here we've got f and p of theta. And what we're going to do is we're going to try to sample from f of theta, and we may have an idea of what it looks like, but we don't have an analytical function for it. Let's take something crazy. Let's say that f of theta is something like this with multiple modes here. So we're going to call this red line. This is f of theta. What we want to do is, the way the accept-reject sampling works is we're going to start by proposing theta values. And what we need in order to do this is a so-called proposal density. So for example, I might propose values of theta out of the normal, like that, okay? And the key here is that the proposal density has to have a greater density value at every point theta than the target. Now, it's very, very uncommon for the raw proposal density to have this property, which is why we do this thing called create an envelope function, where we just multiply the proposal density by some constant to raise to raise p of theta above f of theta for all points theta. So I can just, literally multiply the density by some constant in order to make this true. That can make the envelope function no longer a proper distribution, which is to say it will no longer sum to 1. As you're going to see, that's actually not important. The proposal density does need to be a proper density, but the envelope function doesn't. Okay, so we've got our envelope function and our proposal density. What are we going to do? Now, all we do is first draw a bunch of candidates. We can think of doing this in sequence. Draw a candidate value theta I out of the proposal density. So we say, okay, I'm going to draw a bunch of samples, and the first one maybe is going to be here. This is my first candidate. So what I want to do is say, should I accept or reject this as a sample from f of theta? Well, what I'm going to do is I'm going to draw a value from the uniform density, and I'm going to accept theta I, my candidate, as being a sample from f of I if u of I is less than f of theta divided by e of theta. That's it. That's all I'm doing. And that's really the end of the accept-reject algorithm. Just do that 1,000 times or 1,000,000 times, however many samples you need. Accept the ones for which your uniform value is less than that ratio. Reject them otherwise. The end. That's it. So, and it turns out that as the number of times you repeat this process gets very large, in this case I have it noted here going to infinity, but obviously you don't actually have to go to infinity, you just have to get to a very big number. The collection of accepted theta I values will follow the distribution the target distribution f of theta. Maybe this intuitively occurs to you why this is happening, maybe it doesn't. Let me try to give you a sense of why this procedure works. what we're doing is using the proposal density to generate a ton of thetas, and then we're going to accept those thetas into our proposal based on how likely we were to propose them relative to how likely they are to be in f of theta. So for example, here in my first candidate, theta I, I've got a pretty good bunch of, I've got a pretty good f of theta for that value. I'm also reasonably likely to propose it. So I'm going to accept this a little more than half the time, in the sense that my proposal density is a little more than twice what my target density is in this case. If I were to have proposed another candidate, say this one right here, now this is theta j, another candidate. Now I've got a fairly low presence of that in my density function, and I'm actually fairly likely to propose that, and so I'm going to reject that much more often. If I do this over and over and over again, rejecting and accepting relative to the ratio of presence in the target distribution as compared to presence in the proposal distribution, I will over time build up a bunch of samples that look like the target distribution. That's the best way I can think of to explain how this works. It's easy to say that it does work. I can show you in R, and I will very shortly, that it does work. But that's why it works. Now you may be saying to yourself, what if I've got a theta that's multidimensional? I mean, I've sort of illustrated this for a one-dimensional theta, which is all fine and dandy, but what happens when theta takes on multiple potential values? Well, if theta is multidimensional, you can just choose a multidimensional proposal density, like the multivariate normal, which is known in Stata, or the uniform distribution. A multivariate uniform is just a combination of multiple bivariate uniforms, or univariate uniforms, I should say. And draw candidates from every dimension at the same time, and then compute the ratio and accept or reject accordingly. In other words, you just replace one-dimensional f with a multidimensional f, and you replace a one-dimensional p with a multidimensional p, and you have an accept-reject algorithm in multiple dimensions. So the accept-reject algorithm is a way of getting from a simple density like like the normal. Well, it's not actually that simple, but it's simple in the sense that R implements it. Or maybe the uniform density, which is very simple to sample from, to more complicated densities like this multimodal red thing I've got here. And I can use my simple distributions to allow me to draw from more complicated distributions. So let's see an example of how this works in R. Well, as you noticed, I magically changed shirts between now and the last video, and I'm going to magically change back in the next frame. The reason that happened is I've decided to re-record a bit of this part of the lecture because I have a better example than I did last time, with a couple of additional tweaks and a few fewer technical problems. But let me start off by showing you the very simple process of Monte Carlo integration. And I call this the very simple process because this is a very simple toy example that's sort of designed to work in a case where, in fact, we could probably integrate via other means like quadrature. Not analytically, actually, but by quadrature for sure. And any number of standard processes will get the right answer. And it's the fact that we can integrate this problem by other means is going to allow us to check our answer from Monte Carlo integration against the other method to make sure that we're doing it right, which is always a nice thing to do whenever you try a new thing. So what I'm going to do is first clear the memory. It's always a good idea to clear your memory when you're getting ready to run some code. And I've saved a vector here called draws. And draws is just a series of numbers from 100 to 10,000 that tells R how many samples it's going to take from the target distribution in order to perform the Monte Carlo integration. And as you might expect, the more draws that you take from the target distribution, the more accurate your integral will be. And taking multiple different values of this draw, these number of draws, is going to allow us to assess exactly how accurate we're getting, both compared to other runs of the Monte Carlo integration with fewer or more draws, and also compared to a completely different method of integration using R's integrate function. So I've got this draw vector set out, and what I'm going to do is for every entry in that draws vector, I'm going to draw that many samples out of the normal density with a mean 0 and standard deviation of 1, the so-called unit normal. And then I'm going to calculate the area between negative 1.96 and 1.96 by simply summing up the number of samples I've taken that are in that range and dividing by the total number of samples I took. Now, again, this is yet a third check on the accuracy of the problem, because this is a very canonical problem in statistics. Almost every statistician knows by heart what the area of the integral of the normal is between negative 1.96 and 1.96, because it's a 95% confidence interval that puts 2.5% in each tail. So the integral should be 0.95. We already know that. So first of all, our Monte Carlo integration should give us an answer of 0.95. Secondly, it should be getting more accurate as the number of draws goes up. And third, it should give us the same answer as this alternative routine, integrate, which is built into R. R just calls the function you tell it. In this case, f is d norm. You give it a lower and upper bound for the integral. And I have to specify for this normal function what its mean and standard deviation are. Actually, integrate can use several different kinds of algorithms. You can specify inside of integrate which algorithm you want to use, but the default's going to work fine here. And that should also give us 0.95, assuming everything's sort of sane here. So this code takes just a second to run. In fact, it's already run. It's very, very quick. And if I now plot, here we go. Here's my estimated area under the curve versus the number of draws that I take in by Monte Carlo integration. And I'm going to add, using this add-line command, a dotted line at the true value, as computed by integrate, which we know should be about 0.95, and what a shock, it's exactly 0.95. That's good news. So what do we see here? Well, what we see is the number of Monte Carlo draws that we take under this distribution grows. The error associated with our integral gets smaller and smaller and smaller. So that's good news. Our Monte Carlo integration procedure is generally speaking accurate, and it gets more and more accurate as we increase the number of draws. In fact, if we wanted to, we could probably make this arbitrarily accurate by just ramping up the number of draws to an enormous number, 100,000, a million, as many as we need to get to an arbitrary level of accuracy. So Monte Carlo integration works, that's reassuring. And for this simple problem, we don't need it. There are other things we can do. But for more complicated problems, calculating integrals using draws is going to turn out to be a very convenient way of computing certain probabilities, certain likelihoods, 95% confidence intervals, for example, or 95% credible regions in the Bayesian sense. And the key thing that's great about it is when you're conducting a Bayesian analysis, typically speaking, you already have these draws in hand because you had to take them in order to figure out what the posterior density looks like. So Monte Carlo integration comes naturally to a Bayesian analyst because it's using something we're already going to have lying around once we finish our Bayesian analysis. It's very convenient. And it's going to be available for problems that for which we can't simply use integrate. We can't simply use R's built-in routines or quadrature or some other technique in order to get the answer. So it works, it's great, and now we can move on to using it in our future analyses. Now I want to talk a little bit about accept, reject sampling. I've said this is another target density, but in this case it's just the target density. The target density I'm going to try to take samples of using accept, reject sampling is a tent distribution. What does the tent distribution look like? Well, I'm going to plot it for you here. And let me go up here and clear my memory, set the seed and everything. There's the tent distribution I'm going to take samples out of. This is a weird-looking but proper probability density. And what it says is that the most likely values come out of 0. All the values come out of some range between -2 and 2. The maximum density is 0.5 at the single mode of 0. And anything outside the range has probability 0. Now, this is a very weird-looking, funky density, but a proper probability density. It has all the characteristics of density. It integrates to 1, for example. The area of a triangle is just 1/2 the base times the height, for those of you who were in geometry. Hopefully all of you, right? So the base is 4, the height is 1/2. 4 times 1/2 is 2, half of that's 1, integrates to 1, that's good news. So 1/2 base times height gives us an area of 1, exactly what we would expect from a probability density. Now, I had to do a little bit of programming to make this density happen. All I'm doing here is just creating a function called tent that returns the density of the distribution. And what I had to do was I gave it 3 parameters: the point at which we're evaluating the density, where my mode is, where the center is, and how wide I wanted that density to be. And this width is actually a half width. It's the distance from the mode to the edge. Excuse me. So from then on, the program does the rest. It calculates first how high the highest density will be given the mode and width you specified. Really, the width is the key here. What the lower and upper limits of the density will be given the width and mode you specified. And then for all the x arguments, it simply says, well, if x is inside of the limits, it's bigger than the low limit and less than the high limit, basically compute a slope and figure out where on that slope between right here, the bottom edge, and right here, the top edge, we are. That's going to be your density. And if you're outside the range, then your density is going to be 0. And whatever you get, just feed that back in a vector. So you can see I used it here to plot that density real nicely. Everything's working great. Now, that's a very odd density, and there may be some program to sample out of it. Probably there is somewhere. Somebody's developed it. It might even be built into R. But it's certainly not one of the typical usual densities that we think about and teach, like the normal or the logistic, or even something like the Cauchy, which we're going to discuss multiple times later. It's a weird one, and accept reject sampling is a thing that we can do to sample out this distribution, despite the fact that we don't have a program in our back pocket to do that. So what I'm going to suggest as the proposal density is the normal. And like I've got a note here, a normal proposal density can never be bigger than the target, including in the tails. So in this case, we've got an easy example because the tails of this density are actually go to 0. They hit 0 outside of the range. So all we need is a density that covers, a proposal density that sort of covers the target density, the tent density here. And what I've done is I've just multiplied the normal density by 1.3 in order to make it cover that. Now, I could have gone higher. I could have, for example, made it 1.8, and then the normal density covers that all the more. I could have spread out the standard deviation of the density to 2, like that. Well, now it's the peak's cut off, so we need to raise it up again. But both of those things are just going to result in a lot of wasted draws. Remember that the goal here is to propose candidates for the target density out of the proposal, and then reject them at a rate equal to the ratio between the height of the density and the height of the target and the height of the proposal density. So what we really ideally want is a proposal density that's very tightly matched to the target density. And, you know, this is not exactly an exact match. You know, there's a gap between the proposal and the target. And there's some gaps here in the tails too, but it's far from terrible. And as you can see, it's actually going to work just fine. So what I can do here is I'm going to draw 40,000 proposals. And the proposals are going to come out of the normal density with a mean of 0 and a standard deviation of 1. And I'm going to decide whether to keep those proposals by computing the accept-reject ratio. So the density of the tent divided by 1.3 times the density of the proposal. Or I'm sorry, yeah, the density of the proposal density, which in this case is the norm. So I've got 40,000 candidate points that I'm drawing out of the normal. And then I'm going to decide whether to keep those points by computing the accept-reject ratio. I keep them with probability equal to the ratio. So this last bit, this keep, basically rolls a dice and says, if the dice comes up favorably, keep it. If it comes up unfavorably, don't keep it. And what I'm doing here is just drawing a single draw from the uniform, like so. Oops, I gotta tell it how many I want. Just one, say for example, comes up 0.22. If that's less than the accept-reject ratio, I keep it. If it's bigger, I reject it. That gives me a reject probability exactly equal to the decision, the accept-reject ratio. Because remember, because that proposal density is higher than the target, the ratio is always going to be between 0 and 1, that minimum 0, maximum of 1, which means that the uniform draw that we take, that we just took right here, has a proposal has that ratio probability of ending up less, and 1 minus that proposal density ratio of ending up bigger. So we have a situation where we're getting the right acceptance and rejection rate. So I'm going to just do this. It only takes a second. And then I'm going to plot the samples against the target density. And, oh, actually, that's spectacular. You can see that the target density is it's dotted line here, dashed line. And the actual samples that we drew are the solid line. And, in fact, they're so close to one another that you can't tell the difference. That's a pretty good-looking triangle. So accept-reject sampling works. That's great. Now, the problem is accept-reject sampling works, but there's some caveats. And the caveat, which is actually, this is why I decided to change the video, because this is the distribution I used last time. There's a caveat that with, for example, the Cauchy. So here's the Cauchy density, and let me plot this Cauchy density for you. It looks like kind of like a normal. But there's some weird characteristics of the Cauchy. For example, it has undefined variance and I believe also an undefined mean. And these are characteristics that spring from the fact that it has very, very fat tails, very slowly converging tails, which make indefinite integrals over this Cauchy space, the Cauchy's domain, weird. They don't come out quite right. And the thing is, a normal proposal density, which is the logical thing you might consider for this particular case, it doesn't work. In fact, it can be proved, although I'm not going to prove it, but there in the Jackman book and in other references you can find even just by Googling, you'll see that it's really hard to find a proposal density that works for the Cauchy because its tails are so fat. Let me just zoom in a bit here. I've got this plotted from -15 to 15. Let me just zoom in to the most likely values. Let's say -5 to 5. So I'm going to plot this here. Just change this around. Oh, not 55. So here we go. Bam. That's what it looks like. Looks great. Now suppose I try I've actually got a logistic here. Let's start with the normal. I'm going to uncomment the normal. I'm going to go from -5 to 5 just like before. With a mean of 0 and a standard deviation of 3. I'm going to multiply that proposal by 2.5. I've got to tell it 5 to 5. There we go. Now, that looks pretty good. And in fact, inside of this particular range from -5 to 5, it might even, in fact, it will work as a proposal density. The problem is it's pretty rare for us to only want to integrate over a finite domain. At least in principle, we want to capture the entire range of values for which the Cauchy is a valid density, which is to say -infinity to infinity. And as soon as we start zooming out again, so I'm going to zoom back out -10 to 10. There we go. And I'm going to go here -10 to 10. And -10 to 10. What's going to happen is, you can see that as we get further out, the normal proposal density actually dips under the Cauchy. And this is what I was saying. No matter how much I pump up that normal, I can always zoom out further and get the normal tails to dip below the Cauchy tails. So as a technical matter, the normal density is never appropriate, at least in the further accept or reject algorithm, as a proposal density for sampling out of the Cauchy. Now, there are various ways of dealing with this. We could use some kind of weird tent-shaped, funky-looking proposal density in the accept-reject algorithm for the Cauchy, but probably the easiest thing to do is just to use a completely different approach for sampling out of the Cauchy. That is to say, not the accept-reject method. And so a little bit further down, I'll show you how to use the Metropolis Hastings algorithm to sample out of the Cauchy. The Metropolis Hastings algorithm is actually built in some ways on the accept-reject logic, but it doesn't have this particular feature that the proposal always has to be bigger than the target, and so it's going to be easier to sample out of the Cauchy using that process. In fact, there are other more direct ways of sampling out of the Cauchy, which we're just sort of setting off to the side. But if you ever get a chance to study sampling and computational statistics, you'll find that there are much, and actually even taking a look at some of the assigned texts for the course, you'll see there are much simpler ways of sampling out these distributions if the distributions are closed and known. Because the Cauchy is, you can actually sample out of it even more simply in that case. The accept-reject algorithm, on the other hand, is not really going to be very easy to use for the Cauchy because it's going to be really hard to find a technically correct proposal. So, for better or worse, most of the problems that we're going to deal with in Bayesian modeling are not going to be so simple that accept-reject sampling is good enough or complicated enough to derive the requisite samples. But it's a good entree into the algorithms that are of sufficient complexity. And probably the foundation for most of these more complicated algorithms is the Metropolis Hastings algorithm, which I'm going to talk about now. Metropolis Hastings is an extension of the principles behind accept-reject sampling. And its advantage is that it's much better suited to problems where you're drawing from a multivariate distribution, and it can even be adapted in the Gibbs sampler variant, which we're going to talk about in just a few tabs, to cases where the densities of the various parameters do not come from the same marginal densities. In other words, these densities all look different from one another. They all have different distributions. So the Metropolis Hastings algorithm is a way of building a chain of samples, theta t, out of some target density, f of theta. And the chain of thetas is linked to each other member of the chain only through its immediate neighbors. What do I mean by that? Well, the way that we construct the density, we start with some candidate value, and then that candidate value, through a process which I will describe, determines the distribution of the next item in the chain, which then determines the distribution of the next item in the chain, and so on. But there's no link, I should say no direct link, between any two elements of the chain that are not directly preceding or following one another in the chain. So for example, the first, or I guess this is really the second element in the chain, theta 1, is not directly related to the density of theta 4, and vice versa. This chain of samples is called a Markov chain. We're going to talk about some properties of Markov chains in a second, but for now it suffices to note that a Markov chain is a sequence of probabilistic values where the probability of the present value is solely a function on the previous value. So wherever I am in this chain, if I'm in the second or third or fourth stage in the chain, so like suppose I'm right here, the density of the next item in the chain is only dependent on the present state of the chain. Markov chains have the property that the entire history of the chain is in some way encapsulated or represented by the present state of the chain, and so only that present state influences the next future iteration of the chain. That's sort of how a Markov chain works. We'll talk a little bit more about what a Markov chain is and how it works in a second. Metropolis Hastings algorithm generates one, though, and it generates one using ideas from accept-reject sampling. And under appropriate conditions, which are to be discussed, the Markov chain that we construct will have a distribution equal to the target distribution f of theta as the length of the chain n gets infinitely, or really very large, but technically speaking, infinitely large. So how does the Metropolis Hastings algorithm work? Well, just like in accept-reject sampling, we have some kind of proposal density for the next value in the chain, and we should know what that proposal density looks like analytically. Generally speaking, the proposal for the present value will depend on the current state of the chain, which is to say, if I'm proposing a value for the next period, what my proposal density look like will depend pretty much solely on where I am right now in the chain. So the chain has to start with a value, so I just set the first value in the chain equal to some initial value. That could be the a prior mode or a prior average. And then, for as long as I want to make this chain, I repetitively propose a candidate out of the proposal density, compute the Metropolis Hastings ratio, draw a sample of one, just one sample out of a uniform density between 0 and 1, and I make the next element of the chain one of two things. It's either my candidate or the past value of the chain. Those are the two possibilities. If U is less than the Metropolis Hastings ratio, then the next element in the chain becomes my candidate. Otherwise, I just carry the past value of the chain forward an additional iteration, and that becomes the past value of the chain becomes the present value of the chain. That's how the Metropolis Hastings algorithm works. It just does do this over and over, and if the conditions are right, which we'll talk about in a second, the distribution of this chain, of samples of this chain, will look like the target density. Now you can probably see some similarities to accept-reject sampling. In particular, this part of the process here where we construct a ratio and then compare that ratio to a uniform distribution. The idea here is we accept new elements of the chain if they are likely to appear in the target density, if they have a high density, and usually in the posterior we're trying to model here, and they are unlikely to be proposed by the density, by the proposal density. And we accept things more frequently if they appear a lot in the posterior and if they are unlikely to be proposed. We're likely to keep our current value if it's got a very high a higher posterior density and it's unlikely to be proposed. And so we compare those two quantities in a ratio, i.e. the Metropolis Hastings ratio, to figure out whether we should keep the sample we got or move on. And you can see how this analogizes to the idea of accept-reject sampling. What we're doing is we're keeping samples or getting new samples that are very likely to occur under the posterior and that our proposal density doesn't give us very often. And so we want to build up a lot of samples where the posterior is high. We want to not build up so many samples where it's low. And the Metropolis Hastings ratio enables us to do that. Now, so far, my argument that this works is heuristic only. I'm sort of saying, yeah, it kind of looks like accept-reject sampling, and trust me, it works. But it turns out, under the right conditions, we can prove. We can actually prove more formally than we will here. It can be proved even more formally that the Metropolis Hastings ratio, or the Metropolis Hastings algorithm, gives us a chain whose properties look like the target density. How do we know that? Well, let's find out. So in order to be able to talk about whether this Metropolis Hastings algorithm produces quality results, we've got to talk a little bit about what a Markov chain is and the properties that a Markov chain has. And the big question we're interested in here is the Markov chain that results from any algorithm, such as the algorithm I just proposed, the Metropolis Hastings algorithm, does it look like the target density? And in order to answer that question, we're going to have to talk a bit about how Markov chains work and what we get out of them. So as we already discussed, a Markov chain is a series of random variables unfolding over time. And the present state, the future state, the next period state of the Markov chain only depends on its present state. That's the primary property of a Markov chain. So we've got what's called a state space, which is the number of possible realizations of the target variable theta. So for example, theta maybe can only take on values, I wrote this wrongly. Maybe theta can only take on values inside of 0, 1, and 2. Those are the only 3 possible values of theta. That would give us a state space of size 3. Theta has 3 possible states, and we're trying to figure out something about the density of theta, which is to say, like the probability that theta is equal to some particular value. So in this case, what we're really talking about is what's the probability that theta equals 1, what's the probability that theta equals 2, and so on. If that's the kind of situation we're looking at, a Markov chain is pretty easy to conceptualize. What a Markov chain is it's produced by a transition matrix that tells you the probability of changing from state I to state j. So in this case, we've got a theta with 3 particular states, and actually maybe I'll even make it simpler and just make it 2 states. That would make it very easy to model. Here's a 2-state theta. And a transition matrix P, for this case, would just be a 2x2 matrix telling us how likely we are to go from I to I, from I to j, from j to I, and from I to j. So for example, if I is 0.8, that would tell us if we started out in state I, we have an 80% chance of transitioning to state I again. Ij you have to have some probability of going somewhere. So the sum of these two has to sum to 1. So the probability of going from I to j would be 0.2. The probability from j to I does not necessarily have to be symmetric with the probability of going from I to j. For example, we could say that the probability of going from j to I is actually higher, maybe 0.3, maybe even higher yet, 0.4, 0.5. And the probability in this case of staying in j, if we started in j, would be 0.7. So a transition matrix in a Markov chain tells us how likely we are to move from one state to the next. Pi, which is the marginal distribution of being in a particular state, just tells us, okay, 0.2, whoops. Pi is telling us how likely I am to be in state I and how likely I am to be in state j in general. Just, I'm 20% likely in observing this chain to be in state I, and 6 plus 2 doesn't add up to 1. Let's say 0.8. I'm 80% likely to be in state j, and I'm 20% likely to be in state I. The end, period. That's what pi is. Now, if we start off in some distribution of states I and j, and we multiply that by the transition matrix, P, and we get pi back again, which is what I'm telling you right here, then pi is a stationary distribution of the Markov chain. What am I telling you? I'm telling you if there's some distribution of states represented in this matrix, or in this vector, pi, and when I transition, I end up in the same distribution of states again, which means that as many times as I transition, at least for a large number of chains, I always end up with the same distribution of states over and over and over again. Then we call pi a stationary distribution of the Markov chain. So what this is telling us is, as this chain unfolds over time, if there's a stationary distribution pi, then the distribution of elements of this chain will have the form of pi. This is a useful property when we're using Markov chains to sample from a distribution, because what we want to find is a Markov chain where pi is the target density that we're looking to sample out of. So eventually you can see where this is going. We want to find Markov chains with stationary distributions, stationary densities or distributions, that look like the target density. There's an analogous statement for when the state space is continuous. Suffice it to say, all this says is that if I have a transition probability function that tells me the likelihood of going into state xt plus 1 given the current state xt, if I find that f of xt plus 1 is equal to f of xt, actually, let me think about this for a second. Yeah, that's right. It's because f of xt plus 1 is the integral of f of xt times f of xt plus 1 given f of xt. So in other words, if we integrate out f of xt, we get f of xt plus 1. If these two densities look like each other, then we have a stationary distribution of the Markov chain. So in other words, if the density of f of x is the same at every time, we have a stationary density of the Markov chain. And just the only thing we've done is replace the discrete probabilities we were talking before with continuous densities, f of xt, and transition probabilities that are themselves conditional densities, so f of xt plus 1 given f of xt. And if it's not clear, the reason why f of xt plus 1 is the integral of f of xt over f of xt, the integral of the transition probability times f of xt, what this is saying is we have to start in, where are we? We have to start in some state. We have to go to some state given that we started in some state. And so if you integrate out all the possible states we can start in and all the different places we can go, that will give us the distribution of t plus 1. The distribution of states we can be in after the transition. It's analogous to pi transpose times p giving you pi again. If the integral of f of xt times f of xt plus 1 given xt gives you f of xt again, then we have a stationary distribution. Now the next hurdle to jump over is, okay, we know what a Markov chain is, we know that there's this thing called stationary distribution, and we want the stationary distribution to be our target density. How can we ensure that that happens? Well, it's actually fairly easy to make sure that happens, at least for the Metropolis Hastings algorithm. So let's see how that works. So what do we want out of our Markov chain that's produced by our Metropolis Hastings algorithm? Well, what we want in technical terms is for our Markov chain to be an ergodic representation of the target density. What does that mean? Well, that means the following 5 things. First of all, these two constitute an ergodic Markov chain. These properties are about ensuring that it's an ergodic representation of the target density. So the first thing we want is for our Markov chain to be recurrent for all theta under the target density. What recurrence means is that the probability of returning to any state under the target density is 1. What does this mean in practical terms? Look, we want to get samples out of the density for the support of that density. So if, for example, we're trying to study the density of some variable theta, we want to make sure that our algorithm samples theta for all values of theta for which the density is valid. And in many cases, that's theta from negative infinity all the way out to positive infinity. So recurrence means that the algorithm, in this case the Markov chain that's produced by this algorithm, has a probability of returning to any valid state equal to 1. And by probability, I mean the probability of returning eventually. That can be many, many, many iterations of the algorithm. But the probability that eventually it will hit that state at some point in time is 1. So we want our Markov chain to be recurrent. Recurrent for all values of theta that are valued under the target density. We also want it to be non-null for all theta under the target density, which is just a way of saying that we expect the time to recurrence to be finite. Now, as I mentioned in point 1, recurrence can take a long time. The probability of getting back to a state needs to be 1, but that could take, technically speaking, an infinite amount of time to get back there. We want the expected time to recurrence to be finite in order for our chain to be so-called non-null. We want our Markov chain to be irreducible, which is a way of saying that the Markov chain can get to any point in the parameter space from any other point in the parameter space in a finite number of transitions. This is kind of a way of saying that we don't want the Markov chain to get trapped in a situation where it can't get to the entire space once it falls into a hole. Let me give you an example of this. Suppose that we have a two-dimensional sampling process going on. So we're sampling theta 1 and theta 2 through some means. And we start our algorithm somewhere, and we start drawing samples, blah, blah, blah. It starts doing its thing. It's drawing samples. It's drawing them in sequence. And we see that it starts to get trapped right here. Now, that may be fine if it's the case that theta 2 and theta 1 only go in this particular region. But if theta 1 and theta 2 are unbounded, and we find that our algorithm gets trapped in a situation where, whoops, that wasn't drawn quite right. There we go. We find ourselves in a situation where, for example, the algorithm, once it falls into a certain part of the space, it can't get out of that space. It just can't get out of this box. Then we've got a reducible. Sorry, I used the wrong word. A reducible Markov chain. We don't want this to happen. We want to get to anywhere in theta space from anywhere in theta space in a finite number of transitions. In other words, we want to sample comprehensively from the space. Irreducibility is a way of saying we know that that happens. We want our Markov chain, number 4, to be aperiodic, which is that there's a positive probability of returning to state theta j from state theta j following any number of transitions. This is kind of a way of saying we don't want we want there to be a chance of ending up anywhere in this space, given anywhere in this space. In other words, we want a Markov chain that has a positive probability of getting back to where it started, no matter where it transitioned, no matter where it is now. We don't want it to be the case that once you get to a certain point, you can't get back to that point. That's kind of the idea here. And finally, and perhaps most importantly, we want the stationary distribution of the Markov chain to be equal to the target density. Now, in terms of many of these characteristics, we have no direct way of proving that our particular Markov chain is necessarily irreducible and aperiodic, that is to say, ergodic, for every possible posterior that we could be sampling out of. In fact, what we're going to do is propose diagnostics to empirically assess whether the Markov chain that we've made is sufficiently irreducible and aperiodic. But there is a way of showing that the stationary distribution of, for example, the Markov chain produced by Metropolis Hastings is equal to the distribution of the target density. That we can prove. And so now I'll show you just sort of informally what that proof looks like. I actually didn't I don't really like my definition of aperiodicity that I originally wrote down here, so I've revised it according to the Gibbons and Hoeting book's definition that I think is better than the one I originally proposed. It gets really more at the heart of what aperiodicity is about. I think my definition was actually wrong. So an aperiodic, it helps to start to define what a period of a chain is. A Markov chain has period k if the probability of going from state j to state j in n steps is 0 for all n not divisible by d. It should be by k. There you go. What that means is that if, for example, I can only get to a state to a particular state of a Markov chain every 3 periods, every 3 iterations of the chain, that Markov chain has a certain cyclicity to it. It's been set up in such a way that I can't reach anywhere in the proposal density at any time. I have to wait for a certain sort of recurring periodic cycle to occur. As long as a Markov chain has a period of k, period of k equals 1, we say that the Markov chain is aperiodic. Now, that doesn't necessarily mean we have to be able to reach anywhere in the state space immediately. For example, you're going to see when we do random walk proposals that in many cases I'm only going to propose values for the Markov chain that are near to where I already am. The point is I should be able to get back to where I started from in one period in principle. And it shouldn't be the case that I can only get back in some predetermined number of intervals, like every 2 periods, every 3 periods, every 4 periods. A Markov chain is aperiodic if that cyclicity doesn't exist in the structure. So I think that's worth revisiting. This is a better definition than the one I originally proposed that really gets at the heart of what aperiodicity means. It just means that there's no cyclical nature built into the Markov chain process.